Hi everyone. My name is Alabi Adebusola. So I just recently moved to Santa Cruz, and so today I'm going to be talking about dark matter fractions in early type galaxies. So we've had a few talks about this, so it's not a strange concept anymore. And the results I'm going to share today, I obtained them while I was at Swinburne in Melbourne as part of my PhD, and in collaboration with the people I've listed on the screen. So the underlying idea here is that if we live in a universe where structures form via in an hierarchical manner, if we study the mass distribution, we should be able to get clues on how the structures assemble their mass. And then such clues should help us answer these two fundamental questions. How did early galaxies form, and when did they form? For this talk, I'm going to focus on early type galaxies, ellipticals and lenticulars. And I'm going to try to quantitatively describe mass distribution using dark matter fractions and average dark matter density. And you can see with the arrows what I'm going to try to do with each of these parameters. So yesterday, Nicola Napolitano gave us a very comprehensive overview of dark matter fractions in the central regions of early type galaxies, even at relatively high redshift. Yeah. So in the central region, it's been well studied. For example, here I've got a plot from Capillary's 2013 paper within the central 1RE, where you can see the trend as a function of stellar mass of what happens when you look at the dark matter fraction. And it's pretty much obvious what happens as you move from low stellar mass, like 10 to the 10, to the high stellar mass and 10 to the 12. So this, of course, it's relatively easy to do this for early type galaxies in the central region using stellar kinematics or using even strong lensing as been done by August's group. And essentially you get the strength. So this is well known, it's well studied. But that's not the case when you move to the outskirts of early type galaxies. So here, what I have on the screen here is a plot from this in 2012. This is, before my study, this is the state-of-the-art study of what happens in the outskirts of early type galaxies. Because as you move outwards, stellar light becomes very faint. And so you can't really do what, you can't probe the outskirts of early type galaxies with stars anymore. You've got to use some other tracers, some discrete tracers. So in this, Alice Lisson's work, she used globular clusters and planetary nebulae. So the data set is not homogeneous, okay? And you can see, I'm going to try to draw your attention to this plot and just point out two things here. You see that for Milky Way like galaxies, she only has two galaxies here. And as you move even below that stellar mass, this is just an extrapolation. So what I'm going to try to do in this study is populate this part of the plot, and just as a cheat, I'm going to have 15 data points here. So we're going to see what really happens as we move outwards. Now, you might start wondering that why am I using 5RE? Is it just an arbitrary number? It's not really arbitrary. It's because it's informed by the fact that as you look at your galaxy, you see that 1RE is just like a tenth of your scale radius. So if you really want to understand how mass is distributed, you want to move outwards to the regions dominated by dark matter. Just to put everything in perspective, in a 10 to the 11 solar mass galaxy, a 5RE would correspond to something like 30 kiloparsecs in physical scale. Okay, so and then cosmological simulations are now beginning to report dark matter fractions at these scales. So it's relatively easy to make comparisons now. Also, I'm going to talk about the average dark matter density. The idea is that if you understand how your dark matter is arranged within your scale radius, it should be relatively straightforward to infer the epoch of formation of the halo. Now, this is well known. This the halo concentration, how it scales with the epoch of formation of the halo. It's pretty much well known that if you have a dark matter halo where with high halo concentration, it means that halo assembled early and vice versa. But the halo concentration is notoriously difficult to measure. So what we're going to do is we're going to just use our average dark matter density and use this to inform the epoch of formation of the halo. So You might start wondering how are we going to get this data. So we've obtained our data from Slug Survey, and this is just an overview of the properties of what makes the survey unique. What we've done is that we've looked at a sample of galaxies that is not complete but representative in nearby galaxies, and we've got very good velocity measurements out to like 12 ARI. And our velocity measurements are very good. The uncertainties on each individual radar velocity is very small. And that makes, this kind of work relatively easy to do. So here's a summary of just an overview of the data we have. Our data is publicly available. If you look at this, I'll try to draw your attention to this plot. You'll see that at the low stellar mass end, we've got lots of data here, and that's going to help. But you see that we have quite a number of galaxies where the number of spectroscopically confirmed globular clusters, it's less than 100. That means you can't reuse your sophisticated dynamical modeling techniques to actually measure your mass. And that's why for this study, we've decided to use tracer mass estimator. So we're going to trade sophistication in our modeling technique for this method that enables us to get our mass estimates. So essentially, it uses these three. The model assumptions are very straightforward. You've got the projected tracer density profile, which we've compiled results from the literature. We've fed a function to it. So we know how it varies as a function of stellar mass. You make assumptions for the shape of the gravitational potential. Of course, we don't know these a priori. So essentially what we've done is to go to cosmological simulations, for example, the one by Wu et al., and kind of measure the slope of the circular velocity profiles at 5 ARI, and those are these blue points. And then just to be sure that, and use that as to parameterize the shape of the gravitational potential, and just to be sure that we're doing something reasonable, we've also compared to measurements of the slope of the circular velocity from Trujillo Gomez 2011. Those are these brown points. And you can see there's a very good match between what we see. So the last assumption is on the anisotropy, which is not known. And then for the kind of data we have, we can't constrain it from the data. So we just make these prior assumptions. We get our mass at 0.5, and at these other, when it's isotropic, when it's radially isotropic, when we have radial anisotropy, and when we have a tangential anisotropy. So we make other assumptions, and I'm happy to take questions on this later on. But I'm going to just try to point out that we make corrections for rotation, for flattening and inclination. We account for substructures and anisotropy in our results, and you can see the extent of the corrections we make here. Okay, so just to understand what our results are, we're going to compare our results to some simple galaxy model, and just to construct the galaxy models, what we've done is use scaling relations. The stellar mass, stellar mass scaling relation. We combine it with the galaxy size stellar mass relation from Lange 2015, elo mass concentration, galaxy size CERSIC index relation. We assume some Planck cosmology. We assume that dark matter profile follows NFW shape, and we assume that our stars follow a CERSIC profile. And essentially, this is what we get. So pretty much we have a good handle of what we expect from our measurement. So what I'm showing here is just two realizations of a simple model. One, when we use the black line, when we use the size stellar mass relation from Lange 2015, and the green dashed line when we fit a function to our size stellar mass measurement. So you can see that pretty much independent of whatever we use, we kind of know where we're going to fall. Okay, so again, just to have a good idea of what is happening, we're going to compare our results also to expectations from cosmological simulation. So here I'm showing the simulation from Wu 2014, and those are these red points. But the problem with this simulation is that while the shape of the dark matter profile is modified by baryonic processes, they did not account for feedback. So they overproduce stars by a factor of 2 to 3. And, so that's something one should take into account if you're using results from this simulation. But then their total mass is consistent with what we measure. But then it's just that because of the degeneracy between stellar mass and dark matter and mass, they've measured this relatively low dark matter fraction. We also we're going to compare our results with predictions from a cosmological simulation where feedback was implemented. So this is from Ramos 2017, the magneticum simulation. And you can see that you just easily now you can see the effect of feedback. We are now measuring what is more realistic. And here is our result. I've removed error bars from my data point, and here I'm showing a representative error bar. So you can now see that at the low stellar mass end, where previously there was no data, you can see what is really happening now. Dark matter fraction in the outskirts of early type galaxies essentially has more or less a mean value of 0.6, but there's a very huge scatter at 10 to the 11 stellar mass. And this is not strange anyway, because we know this is a magic number and we know what happens there. And I'm happy to have that discussion anyway. What is really curious about this plot is the fact that none of the individual cosmological simulations predict the entire range of values we measure. Okay, so what we can do now is just try to see if there's any correlation between the dark matter fraction we've measured and galaxy properties. So here, what I'm showing here is dark matter fraction as a function of galaxy environment. And when you look at galaxies around 10 to the 11, you see that this huge spread can't be entirely attributed to environment. We can do the same thing with morphology and see, and it becomes obvious that even at 10 to the 11, we've got galaxies with different morphologies. Here, the open squares are just galaxies where the morphology is not well defined. Again, I'd like to point your attention to this, that there appears to be a hint of a trend in our lenticular galaxies, the blue diamond. And you can see that it appears that for galaxies where the disk is significant, it's like dark matter fraction decreases as galaxy mass increases. But you don't find that for the bulge-dominated galaxies, the true ellipticals. This is Phonax A, so that you know that we've not done any fit here, but this is Phonax A. But I would like to point out that we know this galaxy has a recent major merger of two spirals as well. Okay. But this is a hint. Well, we're not going to make any big deal out of this result for now. We just need, I guess, we need more data on this end of a plot to see if this trend is real, or maybe it's just because of the galaxies we've picked to study. So there's a claim made by a recent claim by Couture in Couture 2015 that maybe all galaxies are maximal. What we're seeing in our ellipticals kind of goes against that trend, because it appears that if you have true bulges or your ellipticals, it appears that the trend is that, dark matter fraction increases as your stellar mass increases. Okay, so these are just like, it's like a laundry list of things that could be responsible for the diverse measurements that we see. Okay, but some of them we can easily rule out, but I think it's important to consider these 2 points. One, maybe these galaxies with very low dark matter fraction, and they're just normal galaxies that reside in very diffuse halos, in the sense that when you look at their size stellar mass, when you put them on the size stellar mass plane, they look normal. But then we're measuring very low dark matter fraction, even at 5 Re. Maybe they're just normal galaxies that are, that reside in diffuse halos. Another thing one could consider is maybe dark matter could be self-interacting. So here I'm going to show some recent results from Arena Decintio, and you can see it's these brain stars and the blue polygons. Those are results from a 2017 paper where she compared what happens in Milky Way mass galaxies if dark matter is self-interacting or if it's cold dark matter. It appears that if you have self-interacting dark matter, there's a chance of measuring low dark matter fractions. Okay. Yeah, so I'm not going to have time to really go into this. Yeah. Okay, so what I have is just the other part of my results, where I've measured the average dark matter density within 5 Re. And what I find is that, of course, we're familiar with this point now, but I've also added some points from the literature where the average dark matter density has been measured within very small apertures, from Thomas 2009 for Coma cluster galaxies, and Wegner and Corsini 2016. You can see that there's a trend where your average dark matter density within whatever aperture you choose, essentially this stellar kinematic studies just use a 2 Re aperture. Your average dark matter density decreases with stellar mass, such that galaxies that have higher average dark matter density would form early, and those with low the ones with very low average dark matter density would form late. We could scale this using the coma code from the literature, just to convert our dark matter, the dark matter density to the epoch of formation. And this is a trend we find with size and with stellar mass, such that galaxies that are compact today reside in halos that formed early, and those that are more extended reside in halos that formed late. This is just a typical downsizing anyway, and we know. And when we could put this on this plot where we compare the epoch of formation of the halo with the luminosity weighted age of the central stars, and then we can start making inferences about if the late phase of the mass buildup is dominated by wet mergers or dry mergers. Just to reiterate, here is Phonax A, which is well known to be formed by a major merger of spirals recently. And you can see that from our analysis, it sits here, which agrees with what's been studied in the literature. Yeah. So I'll just put my conclusions up on the screen, and thanks for listening.
Quick question about the modeling.
Yeah.
When you're taking into account velocity and anisotropy, do you have constant beta in the different beta values, or do you allow beta to vary?
No, we fix it. It's constant with radius.
But you try 3 different values.
Exactly. Yeah. We just don't have the data to model. Our data is not good enough, at least at the low stellar mass end, to model variations of anisotropy with radius. And Asha is going to give a talk later where he's going to talk about anisotropy. You know, it's a bit difficult to measure, especially when you don't have good enough data. But then, whatever beta you assume or adopt, the variation is around 10%. So it's not really driving our result. That's just, it's even smaller than the error bars we have on our mass measurement.
I'll ask a question just to clarify. The slug survey is looking at globular clusters, but it also gets light from the same slits.
Yeah.
That's the stars.
Yeah.
And do you see an offset between the stars and the globular clusters? Could that possibly reflect a difference in the anisotropy parameter beta?
Offset in terms of what, please?
In velocity.
We see offsets not within our own data, but if you compare data with, for example, Atlas 3D data, we see offset in velocity dispersion, but not in the rotation amplitude. Yeah. Yep. Nico.
Yeah, did you try to separate the difference from red and blue?
Oh, no, we didn't do that here because again, at the low stellar mass end, we just don't have the data. And then these tracers are just they're tracing the entire gravitational potential.
You can do for time mass.
Oh.
You see whether you can expect that this should be some.
Yeah, that has been well done in the literature. You've got a paper on 5846 on that. Yeah, but and then we've also done is we've compared our results with published results in the literature just to see that we're consistent. And within 0.25 decks, we are very consistent. And that again is comparable to the typical error bars you have on mass measurement. So yeah, it's something. So one of the things we could do is that we could combine globular cluster data with planetary nebula data, especially for the lowest at the low mass end, and then start playing around there. Yeah.
Yes.
So I'm not familiar with
No, we didn't do that. No, we didn't do that. No. Yeah. So one of the things we did is actually, the last plot I showed, we looked at trends with environment, with morphology, with the central kinematics, whether they're fast rotators or slow rotators. Our sample size is very small, so it's a bit tricky doing that here. We just run into problems with numbers.
Okay, let's thank the speaker again.